Hello, I'm Jeff Evenson, and I'm honored to participate at the International Biennale of Glass and to speak with you about a topic I'm passionate about. I'm Senior Vice President and Chief Strategy Officer for Corning Incorporated, which is headquartered in Corning, New York. I'm also Chairman of the Corning Museum of Glass. These positions give me a unique perspective on glass from both a technology and an artistic perspective. I think most of you are familiar with the Corning Museum of Glass. For those of you who aren't familiar with Corning Incorporated, we are a world leader in glass science and related capabilities. For more than 165 years, we've applied our expertise in advanced glass, ceramics, and optical physics to solve tough technology challenges and transform industries. Our innovations include the first glass bulbs for Thomas Edison's electric light, the substrates at the heart of catalytic converters, and the first low-loss optical fiber. We have a long track record of developing life-changing technologies. But I'm not here to talk about my company. Today, I'd like to talk about the life-changing material at the center of this event and at the center of the work we do at Corning. Glass is arguably one of the most transformative materials of all time, and today, it's changing the game for a broad range of industries including consumer electronics, telecommunications, life sciences, architecture, transportation, energy, and more. I'd like to start by describing the properties that make glass such an extraordinary material. Next, I'll review some of the revolutions that glass has spawned and explain why I believe we only recently entered the glass age. I'll end my prepared remarks with some examples of new glass-based technologies that Corning and other innovators are bringing to life. So, what is glass? At its core, glass is quite simple. It consists mainly of silica in the form of sand. But glass is not a single material. It is a diverse family of materials. By adding different elements, you can dramatically change its properties and thereby tune its capabilities for different applications. Let's talk about some of the inherent and achievable properties that make glass so special. I'm sure you already appreciate its aesthetic properties. For more than 3,000 years, artists have used glass because of how it forms, how it feels, how it handles light, and how it takes on color. But glass is also remarkable because of its technical attributes. No one understood that better than Stanislav Lubinsky and Yaroslava Brychtova, who set new artistic and technical directions for glass art and industry in the Czech Republic, and ultimately for glass artists around the world. From new methods for casting architectural glass, to the spectacular optical effects they created by varying the density of the glass and modulating the filtration of light, to the sense of interior volume they produced from the use of thick cast glass, they always balanced art and technique in their work and understood that the improvement of technical skills could create new possibilities for artists. Similarly, at Corning, we believe that an understanding of artistic principles can create new possibilities for technology. I'll return to that thought in a minute, but first, I want to share some examples of the technical properties of glass that may surprise you. For example, glass is one of the world's most stable and enduring engineering materials. Silica glasses get their stability from a continuous network of silicon-oxygen bonds. These bonds remain intact from the time the component sand is mined through the life cycle of the material. That's why glass objects endure for centuries. In contrast, metals corrode and plastic disintegrate and generate toxic chemicals when they burn. Let's consider an example. Have any of you heard people say that glass windows in a medieval cathedral are slightly thicker at the bottom than at the top because of relaxation over the centuries? The reality is, it would take 20 trillion times the age of the Earth for gravity to create a visible change in the thickness of a glass window. Next, glass is virtually impermeable. It's been used for thousands of years as a container because of its effectiveness at protecting contents from contamination by the surrounding environment. A molecule of oxygen takes about 2 weeks to pass through a piece of high-tech plastic 1 millimeter thick. That same oxygen molecule would take 10 quintillion years to pass through 1 millimeter of silica glass. Now, Corning's glass scientists are sticklers for precision, but even our most senior glass fellow was comfortable rounding that number to never. Glass also features unprecedented transparency, which makes it uniquely effective for optical and RF transmission. The glass used for optical fiber is more than 30 times as transparent as the purest water, and only about 1% less transmissive than air on a clear day. If the ocean were made of the glass used in optical fiber, you would be able to clearly see the bottom from every point on its surface. And, despite its reputation for being fragile, glass can be engineered to be incredibly strong and damage resistant. Scientists estimate glass's theoretical strength at more than 15 gigapascals. Now, I realize there may be a few people in the audience who don't measure things in pascals, so I have an analogy that might help. Imagine a scale that measures the pressure under an elephant's foot. To get this scale to read 1 gigapascal, you would need to stack 10,000 elephants on top of each other. Now, since I'm not there in person, I'm unable to stack 10,000 elephants for you, so I won't be demonstrating this point today. But later in my presentation, I will give you a different demonstration of how strong glass can be. Finally, glass is incredibly versatile, which creates tremendous possibilities from both an artistic and an engineering perspective. Artists can mold, cast, blow, or draw glass to create the desired shape because its viscosity decreases in a smooth and continuous manner with increasing temperature, unlike materials that have abrupt transitions from solid to liquid or gas. And, as I noted earlier, scientists and engineers can create a nearly infinite range of new glasses by combining silica with different elements from the periodic table. To date, scientists have added about 50 other elements to silica glass to create unique compositions. But we're just getting started. That brings us to the end of the first section. I've described what glass is and illustrated some of the features that make it really cool. And with capabilities like that, it's not surprising that glass has already had a profound impact on the world. The development of spectacles in the 13th century allowed monks to copy and study religious texts and helped popularize reading following the invention of the printing press. The development of crown glass in the 14th century allowed people to incorporate windows into their homes to let in light while keeping out cold, wind, and rain. The invention of the telescope in the early 17th century expanded our understanding of the universe in which we live. The development of the microscope enabled the discovery of the cell, bacteria, and viruses, leading to life-saving vaccines and antibiotics. Glass mirrors led to the formal use of linear perspective during the Renaissance and encouraged artists such as Rembrandt to paint self-portraits. The development of tempered glass in the early 1900s led to safer military gear and automotive windshields. Glass lenses and picture tubes created major shifts in popular culture by enabling photography, motion pictures, and television. And the invention of low-loss optical fiber in 1970 created the backbone of the internet and ushered in a communications revolution. I think you'll agree that's a pretty impressive list. In light of glass's long history and profound impact on the world already, why do we believe we are living in the glass age today? One reason is the ubiquity of glass and its central role in our day-to-day lives. We interact with glass screens on our computers and smartphones, take pictures through glass lenses, transmit and receive information via glass fibers, protect materials in glass covers and containers, and incorporate decorative and functional glass elements into our homes. But the main reason I believe this is the glass age is because of the journey we've made from magic to science and from science back to magic. Let me explain. For centuries, the Lycurgus cup confounded observers with its mysterious ability to appear jade green when lit from the front and ruby red when lit from the inside. The cup was created in the 4th century, but people didn't understand until relatively recently that the effect was caused by the presence of microscopic silver and gold particles. When monks used early spectacles as reading aids, they didn't understand how the eye refracts light and focuses images. When Murano glassmakers created extraordinarily clear crystal in the 15th century by melting river stones with plant ash, they almost certainly didn't understand how silica interacted with sodium and manganese. People believed that magic was behind all these creations. Today, we've replaced magic with science. We understand how different formulation and fabrication techniques determine the atomic state and structure of a glass. That allows us to precisely control its mechanical, chemical, thermal, and optical properties. Our understanding of glass physics and chemistry also reduces our dependence on serendipity and time-consuming trial and error experimentation. We now use sophisticated modeling techniques to predict how a glass will behave. This knowledge has dramatically accelerated the design and development of new industrial glasses. In the past 10 years alone, glass scientists have unleashed capabilities that we could only dream of a few decades ago. As I noted in the beginning of my remarks, Corning has a 165-year history of glass innovations, yet some of our most recent breakthroughs have happened in relatively quick succession. In the past decade, Corning scientists have developed chemically strengthened glass that can withstand the impact of a baseball traveling at more than 56 kilometers per hour. Let's take a look. That's conventional soda lime glass on the left and Corning's chemically strengthened Gorilla Glass on the right. Both are 1 millimeter thick. Quite a difference, huh? We've also created flexible glass that's slimmer than a dollar bill. Did you ever think you'd see glass that could do this? And we've developed antimicrobial glass that suppresses the growth of mold, mildew, fungi, and bacteria. Of course, we're not the only ones forging new frontiers in glass. For example, the VTT Technical Research Center of Finland has created smart lenses that use optical light guides to display large, high-quality images that augment reality. And scientists at Mosai Corporation in Missouri have developed bioactive glasses that heal flesh wounds by stimulating the body's natural defenses. Pretty cool, huh? The futurist Arthur C. Clarke famously remarked, "Any sufficiently advanced technology is indistinguishable from magic." And I think the latest glass innovations are proving his point. So let's bring it closer to home in the final section of my prepared remarks and talk about some glass innovations that are likely to impact your lives in the near future. I assume many of you are interested in architecture. Glass, of course, has played an important role in architecture historically. I don't think any of us can imagine our homes without windows. And the architect Le Corbusier once called glass the most miraculous means of restoring the law of the sun. But glass has also been criticized for its limits. Let's consider a few. We talked about transparency earlier. Of course, glass can run the gamut from transparent to opaque, but the opacity is generally fixed. Today, a company named View is changing that with electrochromic windows that transition from transparent to opaque on demand. This allows us to eliminate the use of shades. More importantly, it allows us to continuously experience all the benefits of windows and natural light, such as greater productivity in workplaces and healthier environments in hospitals, while increasing our comfort and reducing energy consumption. Another limitation on glass as an architectural component has been its acoustic properties, specifically the unwanted reflection of sounds. We've developed microperforated glass panels that absorb sound and eliminate echo. The front pane has tiny holes in it. The back pane does not. Together, they form a resonant cavity that dissipates energy as air passes in and out of the holes. Absorption is controlled by the hole shape, cavity spacing, and the hole pattern. Lastly, a common complaint about glass, and many other construction and design materials, is the expense of transporting it and the need to process it at specialized facilities. Remember that ultra-slim, flexible glass I showed you a moment ago? That glass has multiple applications for interior design, including backsplashes, modular wall panels, or as a laminate over materials like stainless steel to make them scratch-resistant and easier to clean. The laminates are lightweight, which reduces shipping costs, but they're also extremely durable. And you can use ordinary construction tools like wet saws to cut the glass on site. That means no more waiting for custom orders. Let's take a look. Here, you're seeing a sheet of ultra-slim glass that has been laminated to stainless steel. As you can see, the glass does not shatter when cut. Let's look at a few more examples of what it means to be living in the glass age. Infotainment walls are dissolving the boundaries between the real and the virtual by integrating digital content, social networking, and home and office management capabilities. Interactive retail windows are bridging the gap between online shopping and brick-and-mortar stores, while digital fitting rooms allow customers to experiment virtually. Smart hubs are becoming a reality in the home, allowing you to control appliances, manage calendars, and display images on customizable interfaces. And cars are becoming cleaner, safer, and more connected, thanks to glass that is lightweight, damage-resistant, and optimized for touch technology. Now, those are some of the applications you're likely to see and experience in the very near future. But there are also many exciting glass developments going on behind the scenes to solve some of our world's toughest problems. As we strive to meet the needs of an aging population, glass enables new tools for biomedical discovery and drug delivery. As we try to make our environment greener, glass enables solar technologies to provide cleaner energy. As we continue to improve the way we interact with the world and each other, glass can enable communications with unlimited bandwidth. And as we dissolve the boundaries between the physical and virtual world, glass can enable new display technologies for augmented and virtual reality. Ultimately, glass is enabling a world with cleaner air, more effective medicine, richer entertainment experiences, and more efficient communication. And I think that's a world we all want. So, what will it take to realize the potential of the glass age? Some of the answers won't surprise you. Partnerships are vital. This is something that Lubinsky and Brichtova understood extremely well. Theirs, of course, is one of the most enduring and successful artistic partnerships of the last century. But they also found a way to work effectively within significant geopolitical constraints by partnering with other artists, educators, and industry. As a result, they created opportunities that would not have been possible working in isolation. We need to build bridges in the global glass community between corporations, universities, and professional associations. We need faculty and mentors that create excitement about glass technologies to ensure a strong pipeline of students interested in pursuing glass research. And we need to create collaborations with hardware companies and software developers, information and entertainment content providers, health and human services providers, artists and designers, retailers, and more. We need a healthy supply of funding from government agencies and the private sector, and we need to make sure that the distribution of funding and research is weighted toward the fields that offer the greatest benefits to society. But we need to balance applied research with exploratory research and to allow scientists the opportunity for self-directed projects, because that can lead to the biggest breakthroughs. But perhaps the greatest challenge is one that you can help us with. At Corning, we're pretty good at the technology side of things, but in many ways, our story is still missing the human case. Earlier in my presentation, I mentioned some of the aesthetic properties of glass, the way it forms, feels, handles light, and takes on color. Those features are not only beautiful, they create powerful emotional connections. This is something I experience firsthand on a regular basis. As chairman, I spend a lot of time at the Corning Museum of Glass, including the new Contemporary Art and Design wing. I am constantly inspired and moved by these pieces of art, and I see visitors have the same reaction. Corning headquarters also features glass art throughout the building because of our appreciation for its beauty and because of the positive effect that it has on our people. So my question to you is, how do we not only take advantage of the problem-solving capabilities of this material set, but also get to the heart of humans' fundamental connection and reaction to glass? How can we take this technological moment and create a human moment that helps make the world a more stirring and moving place? I believe that's the real promise of the glass age, and we welcome your ideas. Thank you.